Okay, for this particular section that we have in chapter 5, okay, we are looking at inner product. And if we have letting the vectors u, v, and w be in a vector space V, and we let C be any scalar, well, we're going to have what is referred to as an inner product of V to be a function that associates a real number where we have with the vectors u and v contained, and we're going to have this pairing to satisfy the following axioms. And we're going to have, first of all, we're going to have the inner product consisting of u and v to be equal to the inner product consisting of v and u. And now we have second, okay, so we have with the inner product for a vector space V consisting of u and the sum of v and w. This will be equal to the sum of the inner products of u and v and u and w. And letting C again be a scalar, and if we multiply the inner product of u and v, that is going to be the inner product consisting of the scalar C times u paired with v. And if we have the inner product of v with itself, and it is greater than or equal to 0, and we have that also the inner product of v with itself is equal to 0 if and only if we have the entire vector v to be equal to 0. And for what we have in R2, like what would be regarded as v is equal to 0, okay, in R2 we had the v is equal to 0 and 0, which is equal to 0. So like the pairing we have here, like the 0 comes at front, that'll be in reference to the first component v of 1, and the second 0 will be in reference to the second component where we have v sub 2. And in, say, the R3 space, okay, you have with the vector v, that is equal to 0 as long as we have all the components of v sub 1, v sub 2, and v sub 3 to be equal to 0. Now, looking at an application in determining whether the function defines an inner product on R2, where we have u is equal to u sub 1, u sub 2, and we had the vector v to consist of the subscripted components where we have v sub 1 and v sub 2. And now we have given that the inner product is, or the attempt at the inner product where we have u and v is equal to u sub 1 times v sub 1. Now this is not going to define an inner product on R2. And we'll look at the reason on the basis of what we have in accordance with the axioms. Now the first axiom is going to have that the inner products u paired with v and v paired with u will be equal to each other. Now first of all we have the inner product determination. You have u paired with v, so again we're going to have u sub 1, u sub 2, and v sub 1, v sub 2, so we have, again, we had the product at u sub 1 and v sub 1. And with v and u, okay, so interchanging the order, in case you have v sub 1, v sub 2 at the front, u sub 1, u sub 2 to follow, and we're going to operate in accordance with what we had earlier. Okay, so just swapping places. Okay, so we have the v sub 1 to v sub 2 and the u sub 1, u sub 2 to be interchanging and analogous to what we have with u sub 1, v sub 1 would come out to v sub 1, u sub 1, and those are going to be commutatively equivalent to each other, where v sub 1, u sub 1 is equal to u sub 1, v sub 1. So the first axiom is going to be satisfied. Okay, so the first axiom, failure is not a reason because axiom 1 is complied with. Now for the second one, okay, so we have u and v plus w. So again, we have u consisting of u sub 1, u sub 2, and for v plus w, okay, we're going to have the components. First, we have v sub 1 plus w sub 1, followed by v sub 2 plus w sub 2, and analogous to what we have for u sub 1, v sub 1, which was, again, with the determination of the inner product where u is paired up with v. Okay, so we have with the pairing of u and the sum of v and w. Okay, we have, first of all, we have u sub 1 times the quantity of v sub 1 plus w sub 1, and distributing, so you have u sub 1 v sub 1 plus u sub 1 w sub 1, and that is going to translate to the potential inner products, okay, of u paired up with v and u paired up with w. And so we have the second axiom to be satisfied. Now, looking at what we have in the case of the third axiom, okay, so you have C times the attempted inner product where we have u paired up with v, and now we were looking at C times u sub 1 v sub 1, and that is equal to, upon distributing, say you have C times u sub 1 v sub 1, and then itemizing or grouping together the scalar with u sub 1. So you have, in parentheses, you have C u sub 1 v sub 1, and that is going to translate to what we have in the pairing of Cu and V. Okay, so you have the space consisting of C times U followed by V. Okay, so we have the third axiom is going to be satisfied. Okay, now we have with the attempt at determining whether the fourth axiom is going to be satisfied. So if we have V paired up with itself in the space and in accordance with what we have had with the proposed inner space, okay, of u and v. So you had u sub 1, v sub 1, but where we have the components in u to be replaced with what we have in v. So we have, for v paired up with itself, we have v sub 1 times itself, and we have the square of v sub 1 is going to be greater than or equal to 0. Now, the square of a value in the real number system is only going to be 0 or positive. Now, this statement is true, okay, for v sub 1 equal to 0, but for the entire vector v to be equal to 0, v sub 2 also had to be equal to 0. And to see if the vector v is going to be 0 entirely, okay, well, if I were to determine a non-zero value for v sub 2 and run it through the test, so if I let v sub 2 be equal to 1, so you're going to have 0 and 1, 0 and 1, and guess what? Your u sub 1 v sub 1 will still be at 0 and 0, and the product is equal to 0. But the problematic situation is that for the fourth axiom to pass, v sub 2 had to be limited to only 0, and here we have a non-zero value, and we have the inner space to come out to 0, and that had to work only for v sub 2 to be equal to 0 for that fourth axiom to pass. But since we have a non-zero vector in this case, we had the fourth axiom to fail, and so it does turn out that with a limitation that this particular function does not satisfy the definition for an inner product on R2. Now, let's say that if we have the inner space, okay, now let's say that if we have u paired up with v, and to see if this is going to be an inner space on R2, okay, and okay, so you have this pairing, you have 2 u sub 1 v sub 2 plus u sub 2 v sub 1 plus u sub 1 v sub 2 plus 2 times u sub 2 times v sub 2. And if you notice, we have in the follow-through for the pairing of u and v, I had the following statements. I have 3 u sub 1 v sub 2 upon combining these like terms, and I have plus u sub 2 v sub 1 plus 2 u sub 2 v sub 2. And now for switching the order, okay, for the space consisting of v and u, okay, and following through in accordance, okay, so having u where v was and vice versa, and operating in line with what we have originally. Okay, so you have 2 v sub 1 u sub 2 plus v sub 2 u sub 1 plus v sub 1 u sub 2 plus 2 v sub 2 u sub 2. And if I rearrange the terms and put it in alphabetical order, and if you notice, the first and the third terms are alike, so I have 3 u sub 2 v sub 1 plus u sub 1 v sub 2 plus 2 u sub 2 v sub 2. And if you notice, okay, only the last term is identical, but we don't have the first terms to be quite the same, unequivocally. So just to see if the first axiom is going to be satisfied, and there is doubt here. What we're going to do here is just take a sampling, okay, so we can have that the vector u will be where upon u sub 1 is equal to 1, u sub 2 is equal to 0, and we'll say that for v, we'll have that v sub 1 and v sub 2 will be identical at 1. So if I were to take these components and we have for the pairing with u and v, so you have 2 u sub 1 v sub 2, you have 2 times 1 times 1. And then we have plus u sub 2 v sub 1, so again, u sub 2 is 0, v sub 1 is at 1. And then for u sub 1 v sub 2, okay, you have 1 and 1. And then for 2 times u sub 2 v sub 2, okay, so you have 2 times 0 times 1. And guess what? We have 2 plus 1, which comes out to 3. Now for the space consisting of v and u, okay, so we have 2 v sub 1 u sub 2, so that is going to be 2 times 1 times 0, which is 0. V sub 2 u sub 1 is going to be 1 times 1, which is 1. And v sub 1 u sub 2 will be 1 times 0. And 2 times v sub 2 u sub 2 is going to be 2 times 1 times 0. And guess what? Only the second combination is going to be non-zero, and that product is equal to 1. And guess what? These spaces do not equal each other, so axiom 1 fails. And so this function is not going to define an inner product on R2. Now, if we look in the case of R3, and it says to determine if the function defines an inner product on R3, where we have u is equal to u sub 1, u sub 2, u sub 3, and v is equal to v sub 1, v sub 2, v sub 3, and we have with u and v, okay, in the pairing have 2 times u sub 1, v sub 1, plus 4 u sub 2, v sub 2, plus u sub 3, v sub 3. And I've already said yes. Okay, so looking at the first axiom test, okay, so for u sub v, I have this, and for v sub u, we're going to have just a commutative equivalent where we have 2 v sub 1 u sub 1 plus 4 v sub 2 u sub 2 plus v sub 3 u sub 3, and just switching the order, so I'm back to the space consisting of u and v, and these are equal to each other. So the first axiom is satisfied. And we have with the next, okay, for u and v sub, or I should say u and v plus w, and looking at what we have here and substituting, okay, so we have 2 times u sub 1, and in lieu of v sub 1, I have v sub 1 plus w sub 1, and following through in analogous fashion, okay, replacing what I have with the v with v plus w and the matching subscripts. And what's going to happen here is that the outcome is going to be the space consisting of u and v plus the space consisting of u and w. And then for the scalar, okay, you have distributing c over our expression and itemizing, and this will come out to the space consisting of c times u as well as v. And now for the first 3 axioms, they are satisfied. But now for the last one, okay, for v paired up with itself, now you must have the sum of the squares of the vector components to be greater than or equal to 0. Furthermore, all of the components must be 0. So looking at what we have here and operating in accordance with what we have defined for the space with u and v, and applying the function upon replacing the u at the front with v, so we have 2 times the square of v sub 1 plus 4 times the square of v sub 2 plus the square of v sub 3 is greater than or equal to 0. Okay, and again, squares can never be negative, and the least that the squares can be when added together will be 0. Okay, so if it's not 0, it's going to be positive. But for the sum to be equal to 0, it's going to turn out that all 3 components of what we have for the vector v is going to be 0. So v is equal to v sub 1, v sub 2, v sub 3, and that is equal to 0 since all the components making this up will be equal to 0. And so we had the 4th axiom to be satisfied. So the answer to that particular question, whether this function is going to define an inner product on R3? Again, the answer is yes.